for this invitation. Recording in progress. Great. Thank you for this invitation. I've been enjoying the seminars. I've made a lot of these, and I want to talk to you about one of two projects I have going on that I think are relevant. This one is more kind of classic singular SPDs. The other one is more stochastic dynamics, and I plan to talk about the other one maybe next fall, I think. So what I want to tell you about is some work that actually started a long time ago in the early aughts, but the most recent incarnation of it actually, Marco Romito and I started trying to put some things that we both understood together when we were all at MSRI 5 years ago. And it's taken a while to finally get to this point, but so I'm going to tell you about this work, and it's a joint with, Marco Romito and Longshuan Stu, who's a student at Duke. All right, so let me just start off with a little bit of orientation, how I like to think about this. And I should also mention that this builds heavily on a former student of mine, Andrea Watkins Hairston, and especially this early part builds on my work with her. So if you think about an SD, we all kind of know what ellipticity means, and we all love it when something's elliptic, and that buys us a lot of stuff for free. And so, here I have a simple, I've made it additive for no real good reason. So here's a simple additive SD, stochastic differential equation in Rn for a moment. And that comes with some generator, which, oops, I may have a typo there, but anyway, you know what I mean. I have some generator. And associated with that, I can ask, what's the expected value of some observables, some test function at time t under the stochastic process? So this is some real value test function over here. And of course, this, assuming everything is smooth enough, satisfies this PD, okay? And, when this operator, dt minus L, is elliptic, when it's elliptic, then we have a lot of nice properties. And what I mean by ellipticity for a moment, that's part of the question, is maybe that this quadratic form that I built out of the directions that the noise is forcing has full rank. Okay, so this thing that tells me what directions noise acts has full ranks. And ellipticity is that all directions are acted directly, and hypoellipticity is maybe there needs to be some interaction between the noise, or maybe if it's kind of weak Horomander hypoellipticity, we need some interaction with the lower order part of the symbol. All right. So when you have that, you get some nice things. And maybe one nice thing is immediately that there's a transition density, PT, XY, which is in kind of typical thing is smooth in all three variables. And so it's equivalent with respect to Lebesgue measure, dx. All right. And the question is maybe, whoops, let me come back for a second. Sorry about that. The thing I want to ask you about is, what happens in infinite dimensions when you don't really have any Lebesgue measure, right? I mean, that's the big difference between PDs and ODs. ODs, there's only one topology that most well-behaved ODs live on. They live on the appropriate Lebesgue measure on the space they live in, right? You have to work very hard to make that not happen. The difference in PDs is that somehow all of a sudden, there's all topologies are not equivalent anymore, right? There's R infinity, and R infinity has all these different topologies. And so you have to start worrying about when the right-hand side matches up with the operators, which operators have what domain and how things get mapped into. And, so we do a lot of things like mild formulations, using Duhamel or variation of constants, and to try to make sense of that, to try to match up function spaces. In finite dimensions, we have no problem like that. Okay, so now all of a sudden, if we switch to some SPDs, so now the ODE is now an infinite dimensional ODE, right? It's a stochastic partial differential equation. And we start wanting to ask, well, what about these examples? Okay, so most of this talk is going to be about the top one, but it's worth maybe stopping and pausing about these two for a second. What does non-degeneracy of this bias? And what do we mean non-degenerate, right? What do we mean by non-degenerate? Because it's not just this bounded below by a constant of the identity. There's an identity in all those different topologies that we could imagine. And so which identity it's bounded below by is important, right? So I didn't pick these examples randomly. there's a bit of a program going on here. This is an example that's classically talked about a lot. So the reaction diffusion equations, and in some sense, that's the one that's easiest, because somehow, especially in one dimension, I put 1D here. In 2D or 3D, things can get more complicated. But in 1D, there's a real, the kind of this nonlinearity matches up very well with this nonlinearity, with the forcing term, if we assume, for instance, that this quadratic form is equivalent, like, to some power of the Laplacian, Oops. Right, so sorry, I remember I'm using alpha. So if this is equivalent to some power of the Laplacian, then we actually get a lot of things that look a lot like classical ellipticity theory. And I might call those SPDs truly elliptic. It's interesting to think about what happens if these sigma k's are, again, an eigenvalue of the Laplacian, but maybe with a coefficient that looks like minus k, cubed. Or if you're worried about cubed, make it minus k to the 1,000, right? Just to make my point. All of a sudden, it's not degenerate, the operator, but I can guarantee you that SPD no longer acts like an elliptic SPD. It acts like a hypoelliptic SPD. The kind of the topology that is relevant for that SPD is the topology one gets by hypoelliptic considerations and no longer elliptic considerations. All right. So that's kind of my understanding of how this works. So let me tell you that. So there's some older work that I have from the early aughts with Tufik-Sweden, where we analyze the Navier-Stokes equation, and we can't actually do the Navier-Stokes equation. We have to look at minus the Laplacian to a power 1 plus epsilon. And if we go to 1 plus epsilon and have a requirement like this, that is to say that the covariance operator is equivalent, so bounded above and below, that when you multiply this times that is the bounded operator, right? And it's inverse. So alternatively, if you want to, what I'm saying is that this is a constant minus Laplacian of alpha constant minus Laplacian of alpha. Okay. So when things like that happen, we can't make sense of this equation except by adding we can't prove the kind of theorems I want to prove today, except by adding hyperviscosity. Okay. So somehow Navier-Stokes is critical in this sense. It seems that the nonlinearity makes some non-trivial contributions. And that's something that is kind of a program that I have that we're working on. And maybe the first steps, I'm going to tell you some steps today about Berger's equation. All right. I hope to have actually more results soon, but what I want to tell you about is kind of the first results that show when it acts what I might call elliptically, right? When there's no kind of hypoelliptic effects yet, and showing what the boundary of that is. So,
sorry, is there a relation between epsilon and alpha?
No, that's the amazing. No, there's none. Who was that? Was that Alex?
Slim Ibrahim.
Okay. Oh, sorry, I couldn't see your face. Yeah. No, that's the thing. For Navier-Stokes, it's as long as this decays like a power, right? So this has spectrum. This means that these sigma k's, if I write it in this Fourier basis, these sigma k's look like e to the kx and then some power of k to the maybe 2 alpha. Is that right? I get it. No, it's just alpha. Sorry. To the alpha. As long as it's polynomial, then this is absolutely continuous in a way I'm about to tell you. So now let me say a little bit more about that. So oops, let me just, I forget that when you write on them, then everything goes to hell. All right, so it keeps it. How interesting. All right, that's irritating. I didn't realize that it would keep it. Sorry, I'm trying a new thing today, and apparently that's not doing so good. All right, so I'm not going to worry about that. So the question is that what comes up under here is, and I can't erase, really. I can't erase. How interesting. All right, well, so I'll not write on top of what comes next time. So you might ask, what's under here is what might be considered the PD, the Fokker-Planck equation associated to this SPD. Does that even make sense, right? There's a whole book by DePrato and Zalchek about that. So what I want to talk about, what I want to try to say is, here's these three illustrative examples. So what if I define these semigroups, okay, these Markov semigroups, these transition densities on the function space, and then I say, what if I compare them to the linear equation I get by erasing the nonlinearity? All right, so what I'm doing here is I'm erasing this nonlinearity in each case, and I'm left with this equation, right? All right, so that's my question. So what happens then? So, that's what I'm saying. So if this power here is like, say this, are these two measures equivalent? All right. And so the question earlier about the Navier-Stokes equation, so here I've written in 2D in vorticity form. As long as this alpha is not too irregular, so let's say we have classical solutions, what we have here is we have that this holds. This holds. If what we already proved was we proved that for classical solutions, this also held. These were both works with Tufik-Swidin. But if in this case you actually have something much stronger, what you actually have in the reaction diffusion case, we have that the law of U0t, I called it V, is actually equivalent to the law of Z0t, okay? And so this equivalence is on path space actually for the reaction diffusion. But in these two cases, when we add hyperviscosity here, for instance, this equivalence is actually only at time t. And that's maybe what's novel about the methods I'm going to explain to you today. So they explain how to prove equivalence only at time t, not by using Gersonov's theorem directly, okay? All right, so. And I should say there's a lot of people who've done various work in various directions. Here's some horribly impartial, partial list of them. They're blocked in lines by saying that, these are using methods that might be related to Strong-Feller or some Laplace transform methods. These are using things like Gersonov's method directly. These are going to be using what I might be calling time-shifted Gersonov, which I'll explain what that is in a minute. And that's kind of one of the tools that we've developed to make sense. And that goes back to this work with Tufik and Andrea Watkins. And then Gubinella and Peratowski are the ones thinking about singular SPDs. And that's, again, though, back in the reaction diffusion setting, okay? Not in this setting where we don't have equivalence on the path, but we have, so Burger's is kind of a test case somewhere in between these and Navier-Stokes, okay? And so let me talk about that. All right, so here's the stochastic Burger's equation. Just for compactness and simplicity, I'm going to replace it with this, writing it this way, where A here is minus Laplacian equals A. All right. All right, so I'm going to write kind of in this abstract formulation, and I'm going to go ahead and introduce the operator L on the left-hand side, which just because I'm usually going to think about these equations in their mild formulation. So here I've written it now. So I'm going to usually think about these equations in their mild formulation. And so this, writing L like this, is kind of evocative of that fact that I'm really thinking about inverting this semigroup, the jet semigroup generated by this, and getting the mild formulation here. All right. All right. So let's see. All right. So let me make just some general statements. So in general, I'll always use Q to be the semigroup. The transition semigroup associated with the linear equation, and P will be the transition semigroup associated with the nonlinear equation. All right. So if alpha is less than 1/2, so I'm taking, here's my alpha. My covariance matrix is like a K derivative in space, right? An alpha derivative in space. So if alpha equals, if yes. So if I have a half derivative in space, then kind of you can do in not a very hard way, kind of going back to ideas, simple ideas of de Praton's object, which were great at the time, but they, now we've moved beyond those, that we can prove global existence and uniqueness of classical solutions. In the range 1/2 to 1, we need to do some renormalization, a la Hare and Gubinelli, but we can get all the way up to 1. And if we go all the way to 1, it's a little bit, that's really the boundary case, and that's really where we need the full power of ideas like regularity solutions or the work, by Gubinelli and company, right? So alpha equals 1. So I'll tell you right now, cat out of the bag, I'm not quite going to make alpha equals 1. I'm going to make alpha 1 minus for the moment. All right. So we're in progress, but I'm giving you kind of updated where we are. So let me go and show you. So
Jonathan, may I ask you a question?
Please.
Sorry.
Yeah, Vlad.
Hey,
Vlad.
For the deterministic problem, alpha less than 1/2, you have shocks forming, and when alpha is more.
No, but I have viscosity.
Yeah. So when alpha is less than 1/2, even with viscosity, you have shocks forming.
Okay. Yeah.
And I'm a bit surprised that
alpha. No, I think you have it backwards. I mean, alpha less than 1/2 is very, very. I'm not changing. I'm not changing A here, Vlad.
You're changing the noise. I'm sorry.
Only changing the noise. Yeah. No. Your question is great.
I take it back.
Yeah. Right. Okay. Good. Are we good? All right. Great. Yes, we can talk about that later. I have some thoughts, but not right now. All right. So, So in this range here, we only have local existence and uniqueness up. So we have existence up to some random time, but that time is with positive probability positive. And so up before that time, I have, continuous in time in the soup norm. And I have Holder regularity up to 1/2 minus alpha minus. And when I pass that time, I'll just set equal to death. Mainly because it's fun to get that symbol into your talk somehow. All right. Does everyone understand the question, the setting? So that's what I'm going to be talking about. All right. So here's the main theorem. So for alpha less than 1/2, it already followed from the work of de Prato and de Bouche. And around the same time, myself and Sweden, we did it first for Navier-Stokes in 2005, but the work for Burgers was exactly the same. And Watkins, her thesis really brought this into maybe the way I'm presenting it, closer to the way I'm presenting it today. So think about it. What I said before is it's worth just noticing. It's worth just noticing when alpha is less than 1/2, I have positive Holder regularity in my solutions in space. That's why alpha 1/2 is important. Okay, so I have positive Holder regularity. Oops, this is not going so well, Jonathan. All right, there we go. So here's the theorem. So if I start with any initial data, who cares how rough the initial data is in some ways, but I have that the transition density is absolutely continuous to the Gaussian measure here times a delta measure sitting on the death state, where I put, since it's absolute, since it's equivalence, I can put whatever positive number I want here. This is just to emphasize that if you happen to know that you have global existence or existence past time t, then this part drops out. Okay, that's why I wrote it that way. All right. So that's the thing I'm going to explain to you. So if you want to ask me questions about this, you should ask me now. So the point to notice is alpha less than 1, and its equivalence at time t of these things. All right. So, we're showing that kind of how the burgeoning roughness as we approach the KPZ version of Burgers, right? KPZ is, of course, the Hamilton-Jacobi equation associated with Burgers. So this really is, I'm talking about being in the KPZ setting when I get to alpha equals 1. So, but as I approach up to alpha equals 1, I still have absolute continuous with respect to the Gaussian. Now, it's interesting to think about that because we know that the same Gaussian measure is actually the invariant measure for KPZ. Okay, but it's not quite the same thing. And that's a very algebraic, that's a very rigid statement. And so the question is, here, I don't need it to be exactly this power. I actually it can have variations on it. So I'm assuming that what this means for me for this talk is that Q shares the same eigenbasis as A. That's probably not needed. We can probably relax that. It just would have made some calculations more irritating. But it's non-degenerate, and it's when you multiply K and A inverse, Q and A inverse, you get a bounded operator, and vice versa. A bounded operator is bounded and its inverse is bounded. Okay. All right, I'm going to go forward now. All right, so what's the idea? So we have a couple of different takes on this. We have a third take coming, but I'm going to present two of the takes today. So we're going to do a decomposition across noise scales. So what I'm going to do is I'm going to start off by decomposing that forcing Brownian motion into a sum of Brownian motions. So each of these W's on the right-hand side are independent and identically distributed standard Brownian motions. But I'm going to pick the covariances on the left-hand side so that I have the same covariance. So this is just a particularly convenient way of writing this Brownian motion for me, okay? All right, now I'm going to decompose my linear process, my OU process, into this ladder of Ornstein-Uhlenbach process. So these are each heat equations with different covariance matrices, okay? But because of this assumption, the law of the one on the previous equation page, right, is the same as the law of these, assuming I pick initial data right, okay? All right. So now, similarly, I'm going to decompose the solution into a sum of solutions, xi, t, plus a remainder term. And as notation for compactness, I'm going to say the sum from 0 to n is x0n. Okay, so when I use a superscript like that with two indices, that's just the sum between the two indices. Okay. All right, and now here's the first one. So what I'm going to do is it's going to solve this ladder of equations. All right. Okay, now there's some interesting things to note. This is that this is a feed forward. This is feed forward in the sense that the forcing at this equation at the second level all comes from the first level and the level before. At the nth level, it only depends on the nth minus 1th and the nth minus 2 level. Okay. All right. And then we have this last equation, which is a remainder equation, which the right-hand side for the first time is no longer, conditionally independent of the Brownian motion that's forcing that level, because we have the solution R here. So these are all inhomogeneous stochastically forced heat equations. So the x1 to xn are all Gaussian, in fact, conditionally. If I condition on the levels above, the kth level is conditionally Gaussian. Okay. All right, and so here's the theorem that Longchuan and Marco and I proved, was that that if you pick alpha less than 1, oops, sorry, that's a typo. Ha ha ha. That's a typo. No, that's right. No, that's right. Sorry, that's right. Did I pick that right? Wait a second. So I may have just flipped something, but I'll just check 1 second. I don't want to get it wrong. I think I just flipped something. So with some condition on the alpha, which I'll just make sure that I didn't. I think I just had a moment of stupidity. Yeah. So what happens when you write your slides late at night. Right. Yeah, that's right. So I did flip it. So what I meant to write was alpha needs to be less than this. So you need to exchange these two. Okay. I knew it was wrong. I just all of a sudden flipped out. All right. So if alpha, so pick n sufficiently big to be greater than alpha. Okay. Then that tells you how many levels you need. All right. And then the statement is that there exist choices of a alpha to an. Oh, that's sorry. That should be That's a typo. This should start at A0. This should start at A0 and go in increasing order. Wow, it's a lot of little typos. Sorry about that. So this should be A0. No, sorry. Yeah, this should be A0, A1, and this is AN, okay? And so this one is as rough as the original alpha, but then they decrease all the way down. So this one is less than 1. And then they decrease all the way down to the last one, which is Bn, which is less than a half. And remember, 1/2 is important because that's when we have classical regularity for our solutions, okay? And we'll see that the same is true here, that we'll have classical regularity for that. All right, if that's true, then there exists operators Qn tilde, Qks with this regularity morally, so that you have this conditional X independence, so this conditional equivalence. So the law of the kth level conditioned on what's above it is equivalent to the Gaussian measure at that level. Okay. And so then, whoops. Interesting. Sorry, I was trying to use Keynote and I mean, writing on it, and I may not like it as much as what I usually do. It was an experiment. Sorry to make you my guinea pigs. All right, so that's kind of the main statement of our theorem. Does anyone want to ask me questions about this? This is kind of the technical version of it. All right, so what's maybe interesting is that this decomposition is far from unique. So let me show you. We can do the exact same thing if we now replace. So now you see I've replaced the B's that were the X's that were there with the actual Z's from the Gaussian process. So when I do this, this starts to look a lot more like the tree type constructions, because these are actually all Gaussian objects that one would construct by a tree expansion. All right. So we can prove the exact same thing again with the same typo there. With the same typo. So this one is less than 1. We can prove the same kind of equivalence between the measures. All right, this conditional equivalent, partial equivalence. And what we actually prove is we prove that the X system from the previous slide is equivalent to the Y system. Okay, that's what we prove. And then we prove that the Y system is equivalent to the Z system. We could have, that's not necessary, but it was just what we chose to do because it saved effort. All right. So what we're giving is we're giving a decomposition kind of moving through scales. So we're starting at the roughest scale here. And that's just this system. But by driving the next system and moving down, we can successively show equivalence at each level until we get down to the last level. All right. And then by doing this, once we're at the last level, this is a classical equation, a much more classical equation. It's not quite classical. It has some very rough terms in it, but they're multiplied by some relatively smooth terms. And that product is still good enough to be that we can define it and make use of it and move forward. All right. All right. So everywhere in this whole slide, of course, because of course I just cut and pasted. So I'm going to stop making this correction. Yeah, please.
Sorry, I missed what was ST in the previous slide, in the last equation.
Sorry,
what is S?
S, yeah. So S was the remainder equation under it.
So it's defined there. Okay.
It's the remainder equation. Okay.
Oh, okay. Sorry, I didn't see the L of S. Thank you.
Yeah. Sorry. Yeah. So remember, L of S is my dt minus A operator.
Yes. Thank you.
Yeah. No. All right. So here's the theorem. I've just repeated the main theorem. And really the idea is that because U of t is equal to this sum of these x's plus r, by showing these successive equivalents one layer at a time, unwrapping the equivalents, we can actually find that then U of t is equivalent to the sum of the Z of t's, which was the Gaussian process, the linear process. So that's the technique. I mean, so there's a lot of similarity here with ideas. One thing is to notice, like, going back to the Prato and Zabček, the idea of kind of subtracting off the stochastic convolution and using that to solve the equation, and de Bush and de Prato, doing that for the first time when things became, had some singularity. And then the work by Hare does the same type of things, but the difference is that in those equations, there's not noise ever in these extra equations, because we're only doing kind of classical PD type art statements about being in the right space to make things well defined. We're not trying to prove equivalence of measures. So we have this extra noise that we're carrying around. And another thing that's interesting is that to get all the way to alpha, we need n levels, right? We need arbitrarily many levels, right? This number of levels goes to infinity as we approach 1. And of course, just to do the singular PD, kind of to make things make sense, to remove the singularities, I think you only need 4 levels, right? So to do this absolute continuity argument, we need to do many more slicings all the way up, all right? All right, so yeah, here's the Z. So sorry, I meant to write that. So there's Z, which is the same here. So what we're proving is, by doing this decomposition, we're proving that this is equivalent to this Z, by proving each of these successive Z's is equivalent to their corresponding X. Okay. All right. How am I doing time-wise? What am I? I forgot. What am I supposed to start?
You started the 10 to the hour. So
okay.
you have like 20 minutes.
Okay. All right. So proving equivalence. So just kind of as an example of what one might have, let's think about trying to prove equivalence where I have some function f and some function g. And I want to prove that this process V is equivalent to this process Z, all right? Where I've just picked a generic beta to drive it. So the first thing to notice, of course, is that just by Duhamel, by variation of constants, by linear superposition, whatever your people call it, we have that V of t is just the process Z plus this J operator, which is just the stochastic convolution of this right-hand side, okay? Nothing shocking to this group who do fixed point arguments for a living, right? So here we are. All right, so now, okay, so if f and g, which possibly could be the solution V, by the way, right? They could be the solution V, maybe, right? If they have regularity gamma and delta, then and I should have said that classically, to make sense of this classic, I guess I'll say that in a second. Then it's reasonable to expect that this stochastic convolution has regularity r plus gamma, r plus 1, where r is the min of gamma plus delta. Now, of course, if gamma and delta are both positive, this is just the classical statement about, this nonlinearity here is the product of f and g with the derivative in front of it, right? So I take the product of the two, the product has the smaller of the two regularities, I hit it with the derivative, I lose 1 degree of regularity, I hit it with the heat semigroup, I get 2 degrees of regularity back, and except for just the epsilons about, functional analytic inequalities, I end up with r plus 1, right? So if gamma and delta are both positive, this makes sense. Now, of course, as long as gamma plus delta is positive, we can still make sense of the product, and it has exactly this regularity, all right? Now, one of the things that's one of the kind of key ideas that's used over and over again in various guises, in the works with Hare and Gubinelli and de Prato and de Bush also, and Weber and Murat, various people, right, is the idea that, we can still, even though this product may not be well defined, we can still make sense of this heat semigroup here, this integrated version of it. And we can actually, and when we can make sense of it, it has the exact same regularity we would have had if we just pretended. So in this setting, we can prove that this regularity, that this operator J, this convolution of B with the heat semigroup, has regularity r plus 1 minus, even when gamma plus delta is greater than minus 314. Okay, now I should be careful. I'm not saying this is a general statement, right? I'm saying this in the setting of our problem, because in the setting of our problem, all of our objects are conditionally Gaussian, right? So X is not exactly conditionally Gaussian, but it's, since I told you that it's equivalent to Y, which is actually has Gaussian forcing in it, right? So if we, I think maybe it's worthwhile for me to just, let's see, go back to right here, right? See, if I look at this equation here, the right-hand side, these are all Gaussian objects right here, right? They're all these solutions of these equations right here. So each of these terms is Gaussian. And even when it's X, which is not Gaussian, strictly speaking, we can still make sense of this. Okay, so I'm not claiming that this is a general statement, what I just wrote here, but in this setting, when we need to, we can make sense of this all the way down to -3/2. All right. Okay, so how do you prove absolute continuity? So kind of the classical method when you're in an infinite dimensional sending is the Cameron-Martin theorem. Okay, so the Cameron-Martin theorem says you have a Gaussian measure, you have some deterministic shift of that, you add some deterministic function, and it gives you a sharp condition as to when the Gaussian plus this shifted object, right? So I have this here. It's this Gaussian plus a shift is equivalent to the original law. All right. And if I look in the setting that I've written over here, where R is this number, if R plus beta is positive, then the Cameron-Martin theorem applies. And I'm left, but I need this harsh condition that F and G must be positive, must be independent. Now, in my hierarchy, I designed it so that at each level, the previous levels, they are independent. So I can actually use Cameron-Martin through all of the X's and Y's, all the way down. All right, now when I get to the bottom one, unfortunately, I no longer have this equivalence. I no longer have the independence because the equation Z, remember, the equation, I mean, S and the equation R, these remainder equations were actual equations. They weren't linear equations that had forcing on the right-hand side. They were actually a truly nonlinear equation in the sense that the right-hand side depended on the solution that we were solving for, okay? Is that good? Does anyone want me to go back and show you the equations? Because that's really an important point. All right, so that's exactly the realm that Sonoff is designed for. All right, so Sonoff's theorem says that, in fact, in path space, you have equivalence, okay? You have path, so when I write this here, I mean the variable in path space from 0 to t is equivalent. This plus this as a function of t conditioned on not blowing up is equivalent to the Gaussian measure. And in this case, F and G can be adapted to this filtration of the Brownian motion that's forcing us, okay? So adapted means they don't look into the future, they just depend on the noise up to that moment, right? But the problem is this one. And that's not good enough to apply to Burgers. It's good enough to apply to reaction of fusion equations, but it's not good enough to, in 1D, it's not good enough to apply to Burgers. All right? And it's also not good enough to apply to Navier-Stokes. Okay. All right. So I'm going to explain to you a method that was in these papers from the early aughts by Sweden and myself, and it was also then kind of repackaged and extended and made much clearer by Andrea Watkins, now Andrea Hairston, in her thesis in 2010. And with that modification, which I'll explain to you, we can get all the way down to gamma. We can get back to the same condition as Sonoff's, as Cameron-Martin. All right. F and G can be independent. Now, the one thing is that Cameron-Martin works very well in the setting of singular PDEs because I only need to make sense of this J term. Sonoff, or the time shift of Sonoff, I have to be able to make sense of this B term. So I have to make my equation regular enough that I can eventually make sense of this B term without the convolution with respect to the heat semigroup. And that's why I have to have this ladder of things that pulls me back to regularity, okay? All right, so let me try to explain this idea. So the idea of the time shift to Sonoff is kind of simple. And there's certainly some echoes of the ideas from Bismuth, Elworthy-Lee formula, although not the way it's kind of classically presented. That's David Elworthy and Shumei Lee and Bismuth. So the idea is the following. We're going to write the solution of V. So we already knew that the solution of V was Z plus this J, right? So I'm going to rewrite J in this very simple way. I'm going to factor this into two applications of the T semigroup, okay? And now what I'm going to do is I'm going to lump these together and think of these as my forcing, and these as the semigroup being applied to it. And if I do that, I can do a change of variable. And now I get a forcing which only depends on T over 2 to T. And now it looks like this. Okay, so now I can think of a new equation which has this F, this V tilde that has F applied to it. Okay, now, first of all, this is no longer a diffusion. It's no longer Markovian. There is memory, right? You can check that 2s minus t is less than s for s in the interval 0t. Okay, so this time is only things from the past. So that doesn't bother me. I'm a stochastic analyst part of the time. So it's perfect. Sonoff is perfectly good with adaptive things. So the idea is by making this change, we can then apply Sonoff directly to this equation. And why is that good? Because you see this F here is much more regular. Because first of all, it doesn't go back to the origin. It's 0. This is the indicator function, right? It's 0 on the interval t less than 2. But on this interval, it's been hit by the semigroup. So I get an extra degree of smoothing now, okay, from this object, okay? So I still have a singularity at s equals t at the endpoint that I have to worry about, right? A singularity as the regularization drops off, but it buys me, as usual, an extra degree in my argument, okay? Oops, sorry, let me just actually, sorry. So I just want to say that's where the difference here comes. That's why we have a 1 here and a 2 here. Because this is really Sonoff's applied to this modified equation, all right? All right, and so now let me now tell you how I think about croissants. Okay. So here's T. Here's V0, right? And here's a trajectory. And at every instant of time, what happens is there's a little difference between this equation and this equation, right, which is B. And so what I want to do is I want to absorb the B. I want to make a new Brownian motion, which is this. All right, where Q is, this is Q. Okay. I want to make a new Brownian motion where I shift this thing in infinitesimally. And if I shift it in infinitesimally, then I keep the Z equation on the exact same path. Okay. And that's how you prove the measures are equivalent. And then by this shift has to then be absorbed into the Gaussian measure. And you get a radon-Nikian derivative. It's just completing the square infinitesimally. Okay. That's what's going on. All right. The idea of the time shifted Sonoff is something different. What it says is, okay, so at time S, at time T, I had, or time, let's call it time R, I guess. Let's call it time R. At time R, I had some variation. What I'm going to do is I'm going to, if I want to compare the measures in the tangent space at time T, I'm going to shift to time S equal to T plus R over 2. So I'm going to take this perturbation that I got, and I'm going to shift it forward in time to this perturbation, okay? Because this is just a linear equation with this inhomogeneous forcing, right? Linear superposition doesn't matter. It says I can resum these whenever I want to. I can shift things around in time and space and get the same answer at time t. And the advantage is if I move it forward according to the linearization, according to the Jacobi flow, I get what the equivalent shift should be at time s. And that's exactly what F is. F is simply the shift, the perturbation at time S R move forward to time R plus T over 2. Okay. All right. So that's the idea. And so it's a very, it's a very conceptual idea. And so, I mean, it makes sense. It's not just an algebraic trick. We're actually taking, because we're comparing it to a linear equation, we take this variation that I build up and I move it halfway the distance. And by doing so, I get to smooth it some. And then at this point, I compensate for it and move it into the Gaussian measure. All right. Okay, so that's the idea of this time-shifted Sonoff method. All right. Okay. And so what we're going to do here, so I should say, so somehow the bibliography part disappeared from that last slide. So so that was, first developed, with Tufik Sweden, and then, as I said, Andrea Watkins really did. But Longchois and Marco and I have kind of really pushed it to the edge of what we can do with it. And now we're working to cross over the barrier. So what we're going to do here is we're going to remove each of these terms term by term and collapse them into this term using Cameron Martin. And then we get down to this last term, because now this term is no longer independent of this forcing. It's just adapted because of the presence of this S. I can apply the time-shifted Sonoff here. All right, and I should tell you that the time-shifted Sonoff almost works for Navier-Stokes. It falls short by an epsilon. So there you go. So I think I'm vaguely, I'm even early. Am I early?
Just 3 minutes. It's
3
fine.
minutes. Okay.
Just is fine.
So thanks for your attention. And I don't know what happened. Okay, so I'm sorry. Somehow I'm having syncing issues today. I mean, I think there was something wrong on my end, but my bibliographies didn't come over from my computer, so I'm sorry. We're about to post the paper soon, so I will. You'll see all the bibliography there. Yeah, okay. Please.
So thank you very much. Thank you, Jonathan. And are there any questions?
Jacob looks like he's on an island in Ireland.
Comment?
Not Ireland.
Not Ireland. Maine. All right. So
the picture is very far away.
So any questions?
Any questions or comments? No.
So, Jonathan, if you could sum up in a couple of words. So the main statement shows that you have this absolute continuity with respect to the semigroup induced by the heat equation.
Yeah.
At some meta level, what does that mean?
Well, it means a lot of things first of all, it immediately gives you unique ergodicity, because the transition densities are all equivalent with respect to the same base measure. Right. It also gives you precise statements, about the structure of this equation, right? So let's say you want to know what the Holder regularity is, what the Hasdorf dimension is of the zero crossing level sets, or of the level set crossings for the solutions of the stochastically forced Berger equation. Well, they're exactly the same as the heat equation, right? So any almost sure statement that you want to make about solutions of the equation, right, are actually true about the stochastic equation, about the heat equation, right? Mm-hmm. Right. So you immediately get. So I always think people talk about what the regularity of the solution is when we talk in PDEs. I think that's a mistake. What we really mean is my best guess on the upper bound of the regularity of the solution, right? What I'm actually telling you now is this is the regularity of the solution, right? This is exactly it. It's not above, it's not below, it's not logs. This is it. It's exactly the same as this heat equation, right? And all the spatial properties, any almost sure spatial property is the same, right?
Thank you.